And we're recording.
Okay. Welcome to our regular already colloquium, student colloquium. I took this chance to introduce today's speaker because I'm extremely pleased to do that. This is one of the strongest students that I have ever had in my long years of teaching students. Alejandro is a person who understands mathematics deep enough. He has the right attitude toward mathematics. This is why he asks interesting questions. And one of his questions led him to prepare a proposal for work with McNair for the last summer. But luckily, he was liked by even better people from MIT. And instead of doing the problem in the proposal, he was involved with a piece of very deep and interesting problem, very huge problem, which is related to geometry and topology of symplectic manifolds. And his portion is algebraic, and I'm very happy with this, just because I think he learned algebra mostly from me. But the truth of the matter is that what he's explaining here is related to a very big picture of things that many people, not only at MIT, work on. So that the more we learn from him today, and even, I don't know, anything we learn from him today will be related to a very serious modern mathematics. And I'm very happy to have him here and report on his research last summer. So I'm giving you Alejandro.
Thank you for the kind words. I hope I can live up to expectations. I don't know if everyone here knows me. There's a chair here. But I'm Alejandro Ginory, and he pretty much introduced me pretty well. I can't really follow that up. So this presentation I wanted to give in a way that's different than, let's say, maybe the last couple, the last three. And I just wanted to give you an idea of, this is the first time I've done research. So I wanted to give you an idea of what that process was like, what my experience was like, the way that I thought, and the way that my mind changed just by doing this project. I think that's as important as the raw math material that I'm about to get into. Okay, so first, acknowledgements. So I did my research at MIT. It was called the MIT Summer Research Program, pretty self-explanatory. And it was a group of people, and there were only two mathematicians, and I was one of them. The other one was from Howard University. And I worked with a professor. His name is Dr. Paul Seidel. He's a symplectic geometer, and he does many interesting things. In fact, recently he received an award called the Veblen Prize in Geometry and Topology, something like that, 2010, for doing some sort of algebraic related stuff, categorical stuff related to geometry. So, in a sense, I'm doing an algebraic offshoot of a geometric problem, which is kind of like in his area, what he likes to do. And my immediate supervisor was Dr. Timothy Nugent, postdoctoral fellow actually. Now he's in Stony Brook in the Simon Center, and he does geometry and analysis. So it's kind of like an interesting mixture we had. We had a geometer, we had an analyst, and we had, as I like to smugly refer to myself, an algebraist. So it's kind of like the beginning of a bad joke. So, but it worked very well, and this eclectic combination of people helped me see things in a different way, and I hope that I can express to you all how I came to think differently. So, let's begin. Well, this is where it was. Here's a picture of it. I worked somewhere over there. So this is the only animation you're going to get. Enjoy it. Yes, it's building 2. It's on that side. It's a very nice place. It's a excellent atmosphere. There's a river nearby. It's a nice view. You're relaxed. Yeah, the Charles River. It's a very nice area to do math. You get tired, you leave your office, you go walk around the river, you look out, and hopefully the spirit of Galois or something will inspire you or something, you know. So this is what I hope for.
There are pubs also.
And well,
Like
this
you
is also a
mentioned,
little bit inspirational. So, all right. So geometric motivation. Let's start here. So it starts with a gentleman by the name of Adolf Hurwitz, or as they say on the other side of the Atlantic, Hurwitz. Yes, and he's German, and he was born in the 1800s. There's the date. And he did a lot of things in math that are important. But I'm only dealing with, or I only was related to, the problems related to Riemann surface. In fact, that was his big contribution to Riemann surface theory. Specifically, he cared about covers of Riemann surfaces onto each other. And even more specifically, covers of Riemann surfaces onto the sphere. Now, Riemann surface, let me just quickly say what that means. A Riemann surface is a topological space, or a set of points with a notion of distance that locally looks like the complex plane. Okay, and so he wanted to see how many different ways you could map different Riemann surfaces onto the sphere. And so this is where the entire thing comes from, the entire problem comes from. Now the problem is that Riemann surfaces can get pretty complicated. And so, since they get complicated, you can't have a sort of perfect cover of a sphere. So what ends up happening is that you can have at best, if you have a compact Riemann surface, a sort of almost cover called a branched cover. And it's a cover where there are certain points that are called branch points or ramification points that are kind of like discontinuities. And it turns out that there's a theorem that he proves, it's very nice, that up to a given degree, branch covers of the sphere by a Riemann surface are all equivalent. And they're equivalent up to, there exists a differentiable bijection so that one cover, which is actually a function, can be turned into another cover. So this is the general thing. I didn't deal a lot with the geometry. So what he did, he encoded the information from the geometry into an algebraic problem. And that's what he had me deal with. And I'm not really going to get into that too much because, again, that wasn't really the scope of my research. So, moving on. Here are some examples of Riemann surfaces. This one here corresponds to the square root function, and that one to the cube root function. And that's just examples, so you can have a picture in your head of maybe what we're trying to fit onto a sphere. And we fit it onto the sphere in various sheets, you know, various times over, so they overlap many times. Okay, moving on. So I think I'm just going to get into my project and talk about Hurwitz equivalence. So there's a bunch of writing on the board. I'll go through it. So it turns out that we can encode the information, like I said, from these branch covers of the sphere into these tuples. And let me actually run through what these tuples are. All right. So I'm going to be writing on the board, I think, a lot. So I'll begin here. So first off, we consider L tuples.
Do you have markers, fresh markers?
This is we consider L tuples of elements. So I'll write here. L tuples or tuples of elements of the symmetric group. For those who have taken any course in algebra, you know that the symmetric group is the group of all permutations on n letters. Symmetric group on n letters. With the group action of composition. This is a pretty basic thing. And these tuples have certain characteristics, very important. The first characteristic is that they're product of all of these. So these elements actually are transpositions. So what they do is that they transpose two elements, or two numbers in this case. So, for example, this would be a transposition, 1, 2. And this is the notation we'll be using. And this is actually a function that keeps every number fixed except 1 and 2 and switches them. So for example, 1, 2 of 1 is 2. 1, 2 of 2 is 1. And 1, 2 of m is m for m not equal to 1 or 2. So far so good, right? Alright. So, these are all transpositions in this L tuple. I will remove this example and continue. And the first thing that they need to, the first property they need to have is that they have to multiply out to the identity element of the symmetric group. That's the first thing. And the second thing they need to have is the fact that they have to act transitively on the letters 1 through n, or the numbers 1 through n. What does that mean? It means that if you take the subgroup generated by all of the entries, this should actually equal the entire symmetric group. It turns out that this is equivalent to saying that they act transitively on 1 through n. Okay? So far, so good. Let's see here. So now that we know what we're dealing with, we want to define something called Hurwitz equivalence. This is the primary object that I was dealing with, so I had to become really familiar with these guys. Now, if you were here for the Christian Bueno's presentation, he defined the braid group, right? And it turns out that this Hurwitz move is an action on these tuples. In other words, it changes the tuples in a certain way. It's also called the braid action on an L tuple, right? In this way. And I'll describe it by using words, because that might be a little too technical up there. So let's say you have some L length tuple. And you have one of these sigma I. Now the sigma I are the generators of the braid group of L minus 1. L minus 1 strands. Actually, L strands. L strands. But that's not so important. The important thing is what this thing does to the L tuple. That's really what we care about. So what it does is, it moves the ith position, the transposition in the ith position, to the next position, to I plus 1. Okay? And so I'm going to write it down here. So we have T1, and so on. Let's say this here is the ith position. It moves it to the next one. And so on, it goes all the way to TL. Alright. Now, since it moves it into the ith position, it actually moves the transposition in the I plus 1th position back. Okay? But in doing so, it conjugates it. It gets conjugated by it. And there's a reason for this. I'll show you why in a minute. So in fact, the element that is now in the ith position is the I plus 1th, but conjugated by Ti. Okay? Now why do we do this? Why is this important? Well, this is important because we care to preserve this product. And remember, the product was identity. Now, we can just explicitly calculate this product, and we'll do so. So it's T1, and so on, and then we have this element, Ti plus 1, Ti inverse I, times Ti again, and so on, TL. But these elements here, since this is a group, it has an associative operation. Since it's associative, these two terms here, they cancel. And what are we left with? We're left with actually the original product, Ti, sorry,